morning. So today is the second tutorial on sparse random graphs. Let me first start with, in the first 5 minutes or so, start with what we covered last day. So last day, we looked at a basic model of random graphs, heterogeneous random graph, where you had n vertices and each edge is connected with probability lambda over n. And this model has a phase transition at lambda equals 1. And our main tool was to study relationship between exploding this graph in a breadth first manner and a branching process. We showed that, first of all, the exploration can be upper bounded by a Poisson lambda branching process. So if lambda is less than 1, this Poisson lambda branching process is subcritical. You can use it to upper bound the component sizes. We showed a more general result like maximum component sizes are of order log n, but we did not really prove it. But this shows that you have microscopic components if lambda is less than 1. And the second half, we spend proving the supercritical phase. So if lambda is more than 1, then the branching process survives. And in that case, we have this result. So let Ci be the ith largest component of the heterogeneous random graph. And if lambda is more than 1, then the proportion of vertices in the largest component converges to zeta lambda, where zeta lambda is the survival probability of a Poisson branching process. If lambda is more than 1, branching process survives, right? So this is positive. And the proportion of vertices in the second largest component is going to 0. That's asymptotically negligible with high probability. Well, we did a proof of this, and there were 2 factors in the proof that were important. First was local neighborhood approximation. We said that if we start exploring the graph from a random vertex uniformly chosen, U, then the local neighborhood is approximated by a branching process with high probability. So when the branching process survives, the component is large. So that was the first ingredient. And the second ingredient was if you choose 2 random vertices and their component size is large, then they have to intersect. They cannot be in different components. Okay. So this proof we showed is quite general. So if you have other random graph models where you can verify these 2 conditions, then you can get the same result here. Okay. So how did we verify this for heterogeneous random graph? Well, we started growing 2 neighborhoods from U1 and U2 and showed that after some time, these neighborhoods grow exponentially. And when these neighborhoods have size square root n, they intersect. Therefore, they have to be in the same component. Okay, so that was the recap. So today, I'll be introducing first some other model, let's say more realistic model with more realistic features. Some of them you have been already seeing in other talks. In this part, I will introduce the first models that was introduced to capture these realistic features, summarize the results, will not do all the proofs. Proofs can be done using this technique. So you can verify these techniques. I will mostly focus on getting the local neighborhood approximation. That's it. Not verify the second condition for this new random graph. And in the second part, I want to tell you about percolation and epidemics. In particular, I will try to tell you about a very general result that works for epidemics that is working on a general finite network. Okay, so that's coming up. Finally, if we have time, I will briefly tell you about a fascinating technique in random graph theory that uses stochastic process convergence to conclude about convergence of component sizes. So the technique is really interesting. Hope I get time to do this. Okay. Let me say again, if you have any questions in between, please feel free to interrupt. Okay. All right. Let's start by looking at a few random graph models with more realistic features. So what are the realistic features that occur in real world networks? Okay, there are usually community structures in the network, right? People in same community get to connect with each other with higher probability than between different communities. And also the degree distribution is usually heterogeneous, meaning that they are usually heavy-tailed, the degree distribution. And most often also the graphs are evolving with time. If you look at social networks, people are joining all the time in the social network. These are growing networks. So the first model, one of the first models to capture this kind of things were stochastic block model, configuration model, and preferential attachment model. These are not necessarily the most complex models. These are actually the simplest models that capture these features. So let me start with the stochastic block model. So this is a model with global community structure. Usually this is popular very much in CS and machine learning literature for the community detection problem. Okay. So, but we will not do community detection. We will do the giant component today. So what is the model description? We have K greater than equal to 2 communities. And size of each community, we will denote that by Ni. And we will assume that proportion of vertices in each of the communities is converging to rho I, where some rho I is some positive number. So each of these parts you are seeing is large. They scale linearly with the network size. And number 2 is edges between, say, 2 vertices in different communities arrive with probability Pij over n, and in the same community they occur with Pii over n. So you have a probability matrix that captures the connectivity between different communities. So this divided by n is to make this graph sparse. Okay, and we'll throughout assume that Pij is strictly between 0 and 1. Otherwise, there can be trivial examples, right? Because if Pij equals 0, 2 communities can be completely disconnected and so on. So we'll assume Pij is strictly between 0 and 1. Okay, to find the giant component, the local neighborhood approximation is super important. Let's do the local neighborhood approximation of stochastic block model, right? So we start with a random vertex uniformly chosen. And the random vertex, what is the, let's say, in which community does the random vertex fall? Well, it will fall in the ith community with probability Ni over n, right? Because that's the ith community size, which is by our assumption approximately equal to rho I. So if we choose a uniform vertex, the first vertex would be from community I with probability rho I if you take n tends to infinity. We are doing branching plus approximation, right? So we will take n to infinity. Okay, so uniform vertex in community I appears with probability rho I in the beginning. And what is the neighborhood distribution? Well, if we have k communities, a vertex in, say, community I will have binomial nj, Pij over n many neighbors in the jth community, right? It has approximately this many neighbors because each connections are independent. Well, if I equals j, you have to subtract 1, but let's not worry about that. So the mean is approximately nj times Pij over n. Well, nj over n equals rho j. So this is approximately equals to rho j times Pij. And these are binomials at the n tends to infinity limit. This will become Poisson. So at the next step, you will get vertices of different communities represented by different colors. And the vertice, there will be Poisson rho j Pij many vertices in the next step from community j. Okay. So this is our local neighborhood approximation. And in the next step, this will have further progeny, but the distribution of progeny of this red vertex is different from distribution of progeny of the blue vertex, right? Because they have different connection probabilities to other vertices. So this is not the usual type of branching process that I told you about last day. So these things are called multi-type branching processes. And also there is a theory of studying multi-type branching processes. For that, let's look at the mean matrix Pij star, which is rho j times Pij. And let lambda 1 P star be the largest eigenvalue of P star. Okay. So assume that this so this has positive entries. So P, the lambda 1 P star is positive by Perron-Frobenius theorem. Now, a fact coming from multi-type branching processes is that this branching process will survive if the largest eigenvalue of this P star matrix is more than 1. It will die out if this is less than 1. Okay. Now we have the branching process approximation. We know when the approximation survives or dies out. So we know.
Can you give us some intuition why the largest eigenvalue should come in?
So basically it comes out of a martingale argument. So if you look at the mean matrix, yeah, so you iteratively take powers of the mean matrix, right? At the nth generation, the mean would be m to the power n. So that I mean.
So what you're saying is that if at generation t I have n alpha vertices of color alpha, then the expected number of vertices of color beta is n alpha times p star alpha beta prime. So yes, the expected number of vertices involves the powers of p prime. Yeah, eventually, if the largest eigenvalue is smaller than 1, it dies.
Exactly. And otherwise it survives. Exactly. Okay. Thank you. So this is the condition of our giant emergence. So here is the result, just for sake of bookkeeping. We know that lambda 1 P star is less than 1, means subcritical, lambda 1 P star more than 1, supercritical for stochastic block model. So I will end here actually for stochastic block model because I will cover other models as well. But just wanted to mention there is a more challenging model and more general model actually that is considered in the foundational work of Bolobas, Janssen, and Riordan. In that case, you can have infinitely many types, even uncountably many types. Obviously, dealing with them is a super challenging task. Operator norms show up, but if you are interested in finding more general inhomogeneous random graphs than stochastic block model, check out this paper. Okay.
Is there a nice closed form for the size of the giant component when you have stochastic block model?
Well, you can again use this trick, right? So you can use the fixed point equation. Okay. So it will satisfy this equation probably. Let me try to write 1 minus zeta equals.
Is that the vector now or component? Is that zeta A or is that the vector you zeta?
Yes. So it is actually a vector. It's a, I mean, in the general case, it is a function. So zeta I. So it survives starting from I is 1. This probability is satisfies. No, there is not 1 minus. You have e to the power minus P star matrix zeta, and then so from that you can compute the zeta, and you can take the mean of that, mean of the zeta I, that will give you this zeta.
Okay, so that first thing is a vector of ones then.
Oh, I see. So I have zeta here, so that's why it's confusing for you. So let's say this is zeta tilde. This is the vector. Okay. Okay. So, I mean, essentially, you can do the same trick, right? So you can say that it survives if all its progeny survive. That's how you get the fixed complication. Okay. Next up, models for degree heterogeneous networks. So this kind of networks occur quite often in real world networks. And you can see that there are vertices in the network which has really, really high degree compared to these vertices, for example. So such degree heterogeneous networks with hubs or celebrities are common occurrence. And there are debates on what the degree distributions are. Some people say it's a power law, some people say it's a truncated power law, but one thing is for certain, these are definitely not Poisson, right? So you cannot model them with Eddo-Shreni. So we need a simple and analytically tractable model to study degree heterogeneous networks. And for that, we will introduce this configuration model, which gives you a way to generate graphs with any degree sequence, basically. Okay. All right. What is the model? Suppose you are given a degree sequence d1, d2, dn, and you start out with half edges attached to each of the vertices. So these half edges are potential edges that will be created, right? So from the ith vertex, you always get di many half edges. So the ith vertex always has degree di. We want to keep the degree fixed. So start with di many half edges that is attached to vertex I. And then you can pair the half edges uniformly at random. So you take this vertex, pair it uniformly at random with another one, keep repeating the same trick. You always take any half edge, then uniformly pair it with another. The choice of the first half edge does not matter quite much in the distribution sense, but you can play this game, and at the end you end up with a graph with a given degree sequence. Of course, I have not told you about one thing. It can happen that multiple edges could occur in this graph, right? Or self loops could occur. It could be that you pair two half edges that is associated to the same vertex, or you pair like 4 half edges that are associated to 2 vertices. So those kind of situations, of course, can occur. So at the end, you will, in general, get a multi-graph, not a simple graph. So we will denote this multi-graph by configuration model D. Now, here is the interesting fact, which is why I think it is super interesting to study this in combinatorics. The law of the configuration model, given that the distribution has no multiple edges or self loops, conditional law is same as the uniform distribution over all possible simple graphs with given degree sequence. Right. So if you are trying to, someone has given you a degree sequence, if you are trying to generate a graph uniformly at random, uniform simple graphs, what will you do? So you will try to generate the configuration model. At the first step, you might fail. You might get self loops. So you can repeat it a few times. But when you get a simple graph, that simple graph has to be a uniform sample from all graphs. That's exactly what this is saying. Okay. So the study of this model goes back to 70s. Bender and Canfield and Bolobas was early interested in enumeration problems on random regular graphs using methods from probability, and that's how they came up with this uniform choice model or configuration model. But of course, around 90s, modeling graphs with general degree sequence became super important for different reasons. So the giant component problem also became interesting. The giant component problem for this configuration model was studied by Molla and Reed in 95 and 98. Okay. Are there any questions?
Since we are at the CS Institute, if you do this sampling with projection, how long does it take? Is it polynomial?
Sampling. Well, that depends on your degree distribution. If your degree distribution is really bad, it can take a while. But if your degree distribution has nice properties, I will show you a nice property in the next slide. If your degree distribution is sparse enough, you can generate it pretty fast. Okay, obviously this was a super general model with general degree distribution, and with general degree distribution, it's very difficult to prove results. So we will assume certain regularity conditions, which would seem natural. So for that, let dn be the degree of a uniform vertex. So dn is the empirical degree distribution, right? So it's the degree of uniform vertex. And we'll assume that, first of all, this empirical degree distribution converges to some random variable d in the limit n tends to infinity. Okay, intuitive. We just need the proportion of vertices of each degree converging to some constant. And the second condition is convergence of moments. So expected expectation of this dn should converge to expectation d, and this expectation d has to be finite. Okay, this cannot be infinity. So this condition sort of ensures sparsity, because expectation dn is 1 over n sum over di. That's the average degree, and what we are asking is average degree is converging to a constant. And finally, there can be many trivial situations arise. For example, you could have taken degrees where all degrees are exactly equal to 2, right? So in that case, you will just get a union of cycles, nothing else. So you don't want all the degrees to be exactly equal to 2. So you assume that there are some degree 2 vertices, but there are other vertices as well. Okay. So we want to end up with a complex structure. Well, these conditions are usually easy to verify. Well, if degrees are generated as IID samples, say from a power law degree distribution with finite mean, then these conditions are usually satisfied. So if you look at the literature, there is often another condition that considers something with the second moment. It considers the second moment of the degree distribution converges as well. And this kind of conditions kind of ensures lim inf of the probability that after this uniform generation, you end up with a simple graph. That probability is positive, right? That therefore, so conditional on this event, the graph has uniform law, right? This is just saying that the conditioning event has positive probability. Therefore, if you can prove some, say, concentration results on the configuration model, that the concentration result would carry over to uniform graphs with given degree distribution, as long as you have this condition. But again, this condition can be ensured if you have samples from a power law distribution with just finite variance.
So is this a condition only for fixed degree, or you can allow the degree sequence grow slowly with n?
Great question. So this expectation is over the uniform choice only. So when you sample the degree distribution from power law, then you still have to show that 1 over n sum over di converges, not the expectation converges.
I think you might have asked the question, what if your degree sequence was random? Do you need this? Because if I study some models, I might not have. But there may be probability distribution over degrees.
If degree sequences are random,
Like in your example, they were random, right? You said I sampled degrees d1 up to dn from some given distribution. So you now have a random sequence. So are these convergences in probability?
So that convergence is conditional on the degree sequence. If you have randomness in the degree sequence, you look at the log of this degree of the uniform vertex conditional on this degree. The log converges almost surely with respect to the randomness of the distribution. Does that answer your question?
I guess my question is about this contiguity, the lower bound.
The lower bound.
You have the probability that this random graph model is simple is lower bounded by 0. I think you always need some boundedness on the limit, capital D, if you do that.
Yes.
Have a lower bound. So my question is there any result that even for growing degree, let's say random regular graph growing degree, is it possible? Lower non-trivial lower bound.
Probably bound. That's an interesting question. I don't think the probability is positive in that case. In that case, the probability could go to 0.
So when you have instead, so you're talking about growing average degree,
right?
Which is actually not covered by this notion of local convergence he's talking about. So that actually Jennifer will talk about that on Friday. You need a difference. So his theory covers bounded average degree. So if this is not bounded, you need a different theory, which Jennifer will talk about on Friday.
Yes, thank you.
We can still compute the probability, right? That's just tending to 0. The graph is simple, but you have like e to the minus d. So
yeah, I mean, this probability you can compute exactly for any given degree sequence. But it just
use it in theory, but then you have to pay attention to your statement in the configuration model has to be tending to 1, or the failure probability has to be smaller than the probability that it's non-simple, right?
Yeah, exactly. Thank you.
So you can still use it, I guess, but it's more dedicated.
You need more data.
So in particular, I think Olavash has analyzed that under much more general conditions, because if this is exponentially small, but your concentration is exponentially small with a larger exponent, then you can still do it. You did exactly that. A little bit afterwards, but not very much. Using math that's very similar to this also.
Yes. Okay, let's do the local width convergence, right? So we want to find how the local neighborhoods behave in the limit. So initially we start with a random vertex, right? And therefore that random vertex has degree exactly dn. That's by our assumption. And dn converges to d by our assumption, right? So initially the branching process approximation will have d many progeny. Now the progeny in the second generation is a bit more subtle. Let's do it. So suppose we are in the beginning, we are trying to pair this vertex at the root, and this has r many half edges. But for the rest of the graph, let's divide into different bins. So each bin has, so this one has degree all vertices of degree 1. This one has all vertices of degree 2, degree k, and so on. So there will be a bin with r as well. So in this bin, there are, say, nr. So in this bin, there are n1 vertices, n2 vertices, nk vertices. And in this bin, there will be nr minus 1 vertices, right? Because we have used up one of the vertices. Now, suppose this vertex gets paired to a vertex of degree nk. Then in the next generation, so if it has, so how many half edges will be left? It will have k minus 1 half edges left, right? And those k minus half edges could explore further and give rise to new neighbors. So if dn star is the degree of this vertex to which we pair, the branching process in the, or the exploration in the prelimit will produce dn star many 1 neighbors in the next generation. Now, what is the distribution of dn star minus 1, dn star? Well, probability that dn star is equal to k is equal to, well, it has to pair with one of the half edges in this bin, right? If it pairs with any one of the half edges here, then I will get a vertex of degree k. So there are k in k many half edges in the kth bin. And the total number of choices is just sum over L and L minus 1, because this half edge cannot pair to itself, right? So this is approximately equal to k times pk over sum over L PL, when we know that the proportion of vertices of degree L converges. Is this clear? So I have taken an n tends to infinity limit here. So in the next step, we will already get d star many vertices in the next generation. And probability that d star equals k is given by just what we deduced. And this distribution is often called the size biased distribution. Okay, so branching process produces d star many vertices in the next generation. Good. Now we can, so each of these vertices will be will have d star many 1 progeny. So this is not like a multi-type branching process. This is the same type of process as heterogeneous, but the distribution is different. This distribution is not Poisson. So expectation is just k minus 1 times kpk by normalizing constant, which is the ratio of the second factorial moment and the first factorial moment of the limiting degree distribution.
When you did the limit here, you seem to now have used that the limit of the second axis, because otherwise you wouldn't get E of
to the infinity. You could get to the infinity. So you can't get a branching process that has infinite mean time.
Yeah, but you wrote E of d times d minus 1. So you say if E of d squared would be infinity,
this is equal to infinity,
then the limit must be infinity too.
Yeah. Yes. Yeah. So there can be certainly, but doesn't it follow from this condition that empirical degree distribution converges, right? So you know that empirical degree distribution converges. So the degrees cannot be too badly behaved. So I think if your degree distribution has infinite moment, then the convergence will be also infinite. But I have to
Just wonder whether some uniform integrability or so comes in here to make that work.
So this is the opposite of uniform integrability.
Yes, I know.
This is the opposite of uniform integrability. Problem. But still you can make sense of it if this mean is infinite. You will get a branching process with infinite mean basically. Okay. Therefore, we can talk about survival of this branching process, and this is equal to zeta if this mean that we computed is more than 1, right? Therefore, we again have the giant component result. So if this parameter nu is less than 1, no giant, nu more than 1, a giant has size concentrating size and the proportion of vertices goes to 0. So we just verified the local weak limit, right? In the last slide, we know how the local exploration looks. Of course, you can check the second condition as well to arrive at this, but it is significantly more complicated. So I would like to refer you to see this paper. The giant in random graphs is almost local. Here, this condition is verified for configuration model. But let me end the discussion about configuration model with two interesting cases that you did not see in Erdős-Rényi. First of all, as Christian said, nu can be infinity, right? So if nu equals infinity, for example, if you're sampling your degrees from a power law distribution with infinite variance, then the giant will always exist. So you are in the second regime. And number two is, it can be that zeta is exactly equal to 1. Because, for example, let's consider the case where you have a 3 regular graph. All degrees are greater than equal to 3. Then in the exploration, all vertices will have at least 2 neighbors in the next generation. So the branching process has to survive with probability 1. So this zeta is equal to 1. That is also covered in this theorem.
Is there a nice closed form for this giant size component for different distributions of degrees? Like you have these.
This case or this case?
No, like more general case of like, for example, like a power law that has finite variance as a function of that power.
It's a function of, I guess, again, you can calculate it. So we know how to calculate it, right? So we have the branching process. We can play that same trick. It survives, it dies out if all of its neighbors die out. We can just use that and arrive at our fixed point equation. But I don't remember on top of my head what that is.
So I remember you get actually a 2-step process. So you first calculate the survival probability with this process you decided there. But then the root has a different distribution because the root has the original distribution. So now you have to, but you do the same heuristic. So you express the survival probability of the root in terms of the survival probability of 1 generation down. And now this 1 generation down has a different survival probability, but from there on it's the same. And so you first solve the first and then insert it into the second.
Okay, cool.
And it keeps again explicit equation.
Okay, so that's fixed. Cool, very cool.
All right. Configuration model. Go ahead, please.
Should it also survive this probability 1 if the degree is greater than or equal to 2? Like you need a degree 1.
But that is not covered. In that case, mu is equal to 1. It should survive, but that is not given here. But you don't know how long will it survive. It may if you have a network with, say, on the degree 2 vertices, you will get cycles from it, right? So locally, you may get long cycles, but you don't know. The positive fraction of vertices will be in a cycle. Okay. Done for the configuration model today. Let's end with dynamically growing networks. So around 90s, there was a huge interest in dynamically growing networks coming from biological networks and also invention of internet, right? It was an outstanding challenge in this networks and random graph theory to come up with models that grows dynamically and also produces graphs that have heterogeneous degree distribution. And to model that, preferential attachment model was produced by Barabasi and Albert in 1999. But the ideas that they use also goes back to Yule in 1925. So the idea is rich get richer. So if you have a vertex in the network, which has very high degree, let's say that's a celebrity, if a new vertex arrives, they will have higher chance to connect to the celebrity compared to someone who are not celebrities, right? So the vertices which has higher degree, they will have higher degrees later as well. Initially, they have higher degrees. So this model was first studied by Bolobas, Reward, and Spencer and Tusnadi in the mathematical literature. I will actually mention their result in a short while, but before that, let's see their model. Well, new vertices come with m many connections. Okay, someone comes to the network, they have m edges they can connect to, and in the beginning you start with a graph start with a single vertex that has m self loops so that it does not have degree 0, right? And at time t, vertex vt arrives, and the edges of this vertex vt are paired sequentially, right? And after each pairing, the degrees are updated. So the degree depends on the vertex v, the time when the vertex arrives t, and also where are you in the pairing process, e. Okay. Now the eth edge connects to a previous vertex with probability proportional to the current degree, and it connects to itself. It creates a self loop with probability again proportional to degree, but there is a +1 because without that it will never create a self loop. So connection probability is proportional to the degree in this model. And at the nth step, you have a graph, and each vertex is coming with m connections. So at the end, you have nm edges. Okay. Some first thoughts: if you have m equals 1 connection, so each vertex comes with 1 connection, then you get a tree, and that is called the preferential attachment tree. But in general, you won't get a tree.
You said the first vertex starts with m self loop, so now it starts with 1.
Well, it is a tree with a loop. Sure.
The second substep of the second step, you said it connects to itself with probability something with I. Where's what is the I?
So I, oh, it should be T. Then the typo. And
Why is there a +1? Why is there a +1 for this?
because if that is not the case, initially it has degree 0, right? So it will never connect to itself.
Oh, okay.
But now if m equals 1, maybe you need to modify the law for m equals 1 to get to 3, because it now has also some chance to produce self loops later.
Yes, but I mean,
Exactly.
yes,
right.
yes. So that later you, if you want to create the tree, you will get rid of 1, 1. Okay, the way we have defined this preferential attachment network, it is always connected, right? It connects to already the connected part in the network. So we will not think about the question of giant emergence here again. But the interesting questions are, of course, finding degree distributions and also local neighborhood structures. Let me actually show you what the degree distribution looks like for this model. This result is due to Bolobas, Reward, and Spencer and Tusnadi. So if pkn denotes the proportion of vertices of degree k, and let's say m is greater than equal to 1, then you have this convergence. So pkn converges to some pk uniformly in k. So you get an asymptotic tail bound in n, which is very precise. And what is pk? Well, expression of pk involves ratio of 4 gamma functions, but if you simplify everything, you will get this formula. pk is like c times k to the power -3. So what are we saying here? So it does not matter what m is, the graph will always be a power law with exponent 3, right? In the preferential attachment model. That's the observation. So you get a graph with power law, but not much flexibility. So later there were models defined where there were biases, and in the preferential attachment model where you can get general distributions as well. Yeah. So it is there are variants of the preferential attachment model where you get different power laws. Right. I will skip the proof again, but of course, I want to at least point you to the argument. So proof uses martingale arguments on PKN, and you do the martingale argument, you come up with the Doob martingale, and also bound the differences of the martingale, use the Azuma-Hofding concentration bound. So Azuma-Hofding inequality, that's what is important in order to prove it. All right, we are done with random graphs with more realistic features. We saw three models: stochastic block model, configuration model, and preferential attachment model. In the stochastic block model, we saw that the local neighborhoods are Poisson branching processes. In configuration model, we had to pair half edges uniformly given degrees, and then the local neighborhood was size biased distribution. And in preferential attachment model, vertices come sequentially, and it leads to a power law degree distribution, as we saw. So these are one of the first models to model this kind of phenomena. Of course, you can play around with these models to come up with composite models. In your real world, if you have, say, global communities or degree heterogeneity, you can come up with mixed block models with configuration models, let's say. Right. Up next, I will describe the percolation and epidemics on networks. So percolation is a simple model. Given a graph, percolation refers to keeping each edge of the graph independently with probability P. So at the end, you end up with a random subgraph of the original graph. Now, this looks awfully familiar, right? Because if the original graph was a complete graph, then this is exactly the Erdős-Renyi random graph. However, now the underlying graph can be pretty general. Let's say it will be G. Now, we will be interested in phase transition again. For that, let's define the percolation threshold. Let U be a uniform vertex. Then I will call, there are multiple definitions of percolation threshold, but I will call percolation threshold PC on a sequence of graph Gn. If P is less than PC, then the random proportion of vertices in random components converge in probability to 0. Proportion of vertices, for P more than PC, you have a component that is macroscopic. Okay, so that's the definition of phase transition on general sequence of graphs. And yeah, so this holds for all epsilon positive, strictly positive. Epsilon does not depend on it. So the definition clear?
So wait, what is for set of it?
Set of one.
Set of one.
Yeah. Theta 1. This should be theta 1.
Introduce setup just for people who want.
Yeah, so first of all, there is a typo. It should be theta 1 proportion. And what I mean here is probability that Cu more than say delta, this probability is so the
Divided by.
yes, this probability goes to 1. So there exists a delta such that this probability goes to 1. So you have a component that has linear size with high probability.
Oh, it's omega.
Oh my God.
Set of.
Omega of theta of what?
No, omega
Bigger
of 1.
equals than delta is omega.
Yeah, I mean, there is of course the trivial upper bound that this proportion is upper bounded by 1. So omega and theta are same.
I just want to define setup for people who don't.
Sure, thank you.
So theta of one means just the bounded up below by constants. maybe everybody knows.
So why do you have these epsilons in this? It seems like the equivalent if you just said for p is less than 2p then.
PC can depend on it.
Okay.
For example, in Gaussian random graph, PC is 1 over n. Okay, now let's see the relation with epidemics. So remember the SIR infection model. In this model, an infected person spreads infection to its neighbor independently with probability P. And after spreading the infection for one step, the person becomes immune to the disease. Okay, so that is why it is first susceptible. Persons are first susceptible, then they get infected, but after one step they get recovered. SIR. Okay.
So linked to yesterday's talks, that's the case where the infection time is constantly equal 1.
Infection time is
But the duration of the infection is here just 1 time step, right? You recover.
yes,
after.
yes.
In general, this is a random quantity, but this is sort
Yeah,
of so
exactly.
just to relate to yesterday morning.
Right. Okay. Yeah. Just related to the yesterday morning. Let me re-emphasize that infected person stays infected only for one step, not 2 steps or further. So the same mechanism actually applies for spread of information in social networks, spread of computer viruses, right? So these were some of the questions that we started with yesterday. So what is the relation of this SIR model to epidemics? Well, there is a coupling between SIR model and the percolation model. What is that? Suppose the infection starts at some vertex some vertex V, and it can spread through any edge. So suppose we have a graph. So initially this vertex is infected. At the second step, it could or could not spread to its neighbor. So this vertices, the infection does not spread. These vertices, the infection does spread, and so on. From this vertex also. So after the first step, the vertex at the root becomes immune. In the next step, also you play the same game. Does it look familiar? So this is the exploration process on the percolated graph, right? So the spread of infection is same as the exploration on percolated graph in the SIR model. So the final cluster in the percolation is exactly equal to the final number of infected vertices starting from V. And if the component is large, then the infection would spread to a large population. And people in epidemics are usually interested in this question. That is called the epidemic threshold. And finding epidemic threshold is same as finding percolation threshold. That's what I wanted to convince you. Now I will do calculations with percolation. Now, this is the general result I'm talking about. Suppose you have any connected graph, G, which is finite. Any finite connected graph, let lambda 1a denote the largest eigenvalue of this. Then the result of Dreyf, Ganesh, and Masolier shows the expected component size is less than equal to square root n. Let's pause for a moment and think about this result. This is remarkably general, right? So the graph does not matter. The vertex does not matter. You have, if the probability is less than 1 over lambda a, then the percolation cluster would be at most square root n. Always, it does not matter what graph you are talking about, any finite graph. So this in particular says that your percolation threshold would be at least as large as the inverse of the largest eigenvalue. Now we will do a proof of this on board. So let's say you try to calculate expected cluster size from any vertex V. This is equal to expectation of sum over, say, I indicated that, no, not CV, V.
Can I ask first a question? So this result does not mean that the expected size of the maximal cluster is little over 1n, right?
But I defined it using random vertices, the percolation threshold.
Oh, I see. You didn't ask
Yes.
for the maximal cluster.
Yes. Okay. What does this notation mean? It means that V and I are in the same cluster. So if you look at V and I, there is a path between them. So this is equal to sum over I probability that there is a path between V to I. And so the path can have a length K. So there is a path of length K. And you can take a unified bound over the length of the path. So let's do that. And I think there I should have less than equal to here because I am summing over all I. And then summing over K, probability that V to I has K. So that means that in the percolated graph, you start from V and I, and there will be distinct intermediate vertices such that distinct K minus 1 many intermediate vertices, V1 up to Vk minus 1, such that this path exists in our percolated graph. Now, how many, not how, first of all, what is the probability that any path of length K survives? Can anybody tell me? What is the path, what is the probability that any path of length K survives? Exactly, it's P to the power K. Because each of the edges has to be in percolation cluster, it's P to the power K. And then, oh, I should have written the expectation first. Let's do one more step, just to have our understanding clear. So this is expected, so this is less than equal to expected number of paths, V2 I of length K, right? And this expectation is equal to sum over I, sum over K, P to the power K, and you can take the number of paths in the original graph G, paths of length A. So I think let's do one step more simplification. We can get an upper bound on the number of paths in a graph, right? We can upper bound the number of paths by number of walks. And walks can be computed efficiently. For example, if you take the adjacency matrix and take powers of that adjacency matrix, that gives you walks of length K. So let's do that. So this is less than equal to sum over I, sum over K, P to the power K. Then you take A to the power K, V I. We don't have space here, so it's like what we had there. Expectation of, this is progress. Expectation of CU is less than equal to sum over I, sum over K, P to the power K, A to the power K, B I. I will now erase this. Any questions up to this point? All right, so we can simplify that expression. That expression is equals to, so let's write it in a linear algebra form, right? So this is equal to the matrix P to the power k, A to the power k, sum over k is greater than equal to 1. And you have a sum over I. So on the right, you multiply by the all ones vector. On the left, you multiply by the unit vector that has 1 in the vth place. Okay, the same thing. Now, now we will use our condition p times lambda 1 over a is less than 1. And if this condition holds, the matrix power series of matrices converge. So this would be we transpose A inverse 1. Right. It's just a matrix power series expansion. Well, now we can use the Cauchy-Schwarz inequality. If we use the Cauchy-Schwarz inequality, you would get this is less than equal to, if we transpose the spectral norm of this I minus PA matrix and then the norm of 1 just by the Cauchy-Schwarz inequality. And this is so the norm of this is 1, norm of this is square root n. So we get square root n. And now, if A is a symmetric matrix, I minus PA inverse is a symmetric matrix. So the spectral norm is same as the largest eigenvalue of this matrix, right? Lambda 1 I minus PA inverse. And I can say about the largest eigenvalue of this matrix. So this is equal to square root n 1 minus p lambda 1, which is what we wanted to show, right? So this is less than equal to square root n times 1 minus p lambda 1 over a for any connected graph. Oh, why did we use connectedness? Connectedness is important. The connectedness was used in this step. Okay. If you don't have, so connectedness ensures that the adjacency matrix is irreducible. So first of all, the Perron root is positive, and also you have the power series expansion. Without irreducible matrix, it becomes a bit tricky. All right. So we are done with the proof. And then the natural question is 1 over lambda 1a a good threshold? What kind of graphs are there for which the inverse of the largest eigenvalue is a good threshold? It turns out, yes, this is true for dense sequence of graphs. And it was proved by Bolobas, Borges, Riordan in 2010. So if you have any sequence of dense graphs means proportion of edges scale quadratically with the number of vertices. For any sequence of dense graphs, you can consider percolation on the graph with probability C over lambda 1a. And if you do that, as long as C is less than equal to 1, you don't have any giant. And as long as C is more than 1, you have a giant. So if you have a giant, the component size of a random vertices stays bounded away from 0, right? So this is a very general result. It holds for any dense sequence of graphs. Now, naturally, you might wonder, how about sparse graphs? What happens for sparse graphs? This talk is about sparse graphs, right? It turns out that inverse of the largest eigenvalue is quite far from being the right threshold for any sequence of sparse graphs. Why? Well, so I will not prove this, but for any connected graph, the largest eigenvalue of the adjacency matrix is at most the maximum degree, which just follows from Cauchy-Schwarz theorem. And there is a lower bound also. The lower bound is in terms of average degree and square root of maximum degree. Okay. So what is this saying? So if we have a sparse graph, then this is an order 1 quantity, right? But usually the maximum degree grows. If you have a power law network, it grows polynomially with n. So the inverse of the largest eigenvalue actually decays polynomially with the network. On the other hand, usually percolation thresholds are positive. For example, you can look at simple examples like random graphs. Like if you apply percolation on the Erdős-Rényi random graph, then that stays an Erdős-Rényi random graph. So you can find when the giant emerges. The percolation threshold is the inverse of this lambda parameter. Don't get confused with the eigenvalue here. This is coming from Erdős-Rényi lambda. For the configuration model under regularity conditions on the degrees, the percolation percolation threshold can be shown to be this quantity, expectation d over expectation d minus 1. So if you have finite variance of the degree distribution, this stays bounded away from the zero. So yeah, the inverse of the largest eigenvalue is not quite the right thing to look at when you are considering percolation threshold or epidemic thresholds on sparse graphs, right? That's what I wanted to convince you. Well, for general sparse graphs, what you can do, you can see the graph, percolated graph with on given graph as a random graph. And last time we proved a very general result, like, so if you can show that this percolated cluster, percolated graph is converging locally weakly, and it satisfies this other condition that we have, large components intersect, then you can find epidemic thresholds for sparse graphs. Okay, I wanted to stop there about percolation and epidemics, but does anyone have any questions?
Could you say something if your survival time for the epidemic is actually not constant but a random variable?
So what kind of models are you thinking about?
Yesterday we learned, right?
Oh, right.
You just say, okay, you sort of the burst process is clear again, right? So you have just essentially what happens you get. So you don't because now I have a survival legs. If I infect you, I was more likely to be infected. So my other neighbors are more likely to be infected. So you get a correlation, which is probably true for spread of information or misinformation. If I'm in the mood to write for a long time, I'm more likely to infect you and then more unlikely to infect him. And so the question, and you can write down the burst process, just sort of, again, a simple type burst process, you just don't have Poisson degree distributions. You have some other degree distribution. And I wonder whether your methods can be used to
so I have not thought about this previously, but probably this method can still be used. So this is holds for any sequence of graph that converges locally weakly. So the question is, if you can show that the local weak convergence holds almost surely, and also you can, if you can verify.
Now it will be an oriented graph. I think one will not be the problem. I think two may be the problem, because now you have oriented graphs.
Okay.
So then we don't know what the second condition means.
Okay.
Maybe worth to do a reading group and
Yes,
start a research project.
Yes, that sounds like a great project.
Christian, I have a question to you and perhaps Souvik as well. If you look at a particular I distribution like exponential with intensity lambda, then we can approximate by Poisson. Then isn't it just a double correlation? There will be yet another parameter. Not only the infection ratio, but yet another population on top of the population because of this kind of approximation via Poisson intensity lambda or lambda prime. I'm just asking
But
you.
now it will be correlated.
Yeah. Still kind of for me, because I'm from a discrete world, it seems like maybe one can put kind of another Poisson cloud, which means I twist my intensity with yet another parameter.
Let's take it offline.
Yes.
It's not good for tutorial.
Yes. So in the last 15 minutes, let me finally conclude with a very fascinating topic in random graph theory. And here the convergence of component sizes is shown using convergence of stochastic processes. Okay, so again, I just want to give you the overview of this technique, and this technique is due to Aldous in '97. Well, let's circle back to Erdős-Rényi, right? So we know what happens at lambda less than 1. We know what happens at lambda more than 1. What happens at lambda equals to 1? What happens in between? Well, in the original paper of Erdős-Rényi, it was said that the largest component has size like square n to the power 2/3. But something really very interesting happens at lambda equals to 1, which is different than both of the other regimes. First of all, if you look at all the components have size of order n to the power 2/3. Okay, all the ordered components. So largest component, second largest components, and so on. They have size n to the power 2/3. And number 2 is the limit of the rescaled component sizes are non-degenerate random variables. It is not, you don't get concentration like the giant or in the subcritical region. You get a very different distributions of the component sizes here. And this was proved by Aldous in '97. So the theorem says if lambda equals 1, then if you rescale the component sizes, look at it as a vector that converges in distribution to a non-degenerate random variable. Well, you are talking about convergence of infinite sequences. You have to be careful about topology. So this convergence holds in L2, right? So the description of X will become clear soon. But the thing is, even if you don't care about what happens at the criticality, I think this technique is fascinating. You should care about that. Yeah.
Aldous prove something more, right?
Yes, definitely. Definitely, but I just want to explain. Yeah, definitely. But I just want to show the technique. Okay, the basic idea is to explore the graph and encode the graph in terms of component sizes, encode the component sizes in terms of a walk. So this walk is not the walks on graphs. So these walks are like random walks. Okay. Explore the graph and encode component sizes in terms of a walk, and then take the scaling limit of the walks. And the idea is to recover the scaling limit of the component sizes from this limiting process that we get. Okay. Let me show you one further step. So let's say we are doing this exploration again, but with the exploration, we can keep track of this walk, which at each step adds some new children, -1, -1, because at each step, we are exploring one vertex, right? So we have to remove that vertex in the walk. So you keep on going like that, and eventually you finish exploring the component. And I claim that the first component is explored when this walk hits -1. Why is that? Well, so there is a one extra -1 coming up in the first step. That's why there is -1. So at the beginning of each exploration of each component, you get an additional -1. In the rest of the times, you always get explode vertices, right? So you take the -1 because of the explode vertices. So the whole point here is, if you look at the walk and look at the hitting time to -1, that should give you the component size. If you look at the hitting time to -2, that will be your second component size, and so on. So even if we throw away all the graph and just look at this walk, we can tell what the component sizes are. That's what I meant when I said explode the graph and encode the component sizes in terms of the walk.
What is the order of
I have not said that. That's coming up in the next slide. Any other questions?
Yeah, just to clarify, so these, each time you get a -1, it's like one of the sort of, one of the descendant populations dying out and you're just counting them up?
Yeah,
right?
so at each step, you are getting one, so you have active vertices which have not been explored. So at step, you put one of them in the explored set. But the thing is, at the beginning of each component size, you have an additional minus. That's why you get this. Right. So component sizes are, so this kind of things are called excursion lengths of stochastic processes. Okay. And I just first showed that if you rescale the component sizes, so if you rescale the time by n to the power 2/3 and the space by n to the power 1/3, then this rescaled process converges to a Brownian motion, but not a Brownian motion that has a negative parabolic drift. So if you look at the process, it will look something like this. So you have the walks, right? It hits -1, this is the component size 1, -2, this is the component size 2, and so on. If you take the limit, you will end up with a picture like this. Bad drawing of a diffusion. These are now our limiting component size in some sense. So I sort of will skip a lot of calculations, but everything can be made precise. So the whole idea is that if you can show the limit of exploration processes, you know the component sizes are rescaled by n to the power 2/3 here. Yeah.
No, but you have an excursion which goes far down, and that wouldn't that be very unlikely?
So there is a negative drift, right? So,
but don't you restart your exploration essentially? I mean, the -1 becomes actually a 0.
Yeah, so you can, so what you're talking about, that's looking at the reflected process. I did not define the reflected process. I just looked at the exploration process. If you reflect the process at 0, then you will get what you're saying.
So you say the theorem is true for both the reflected process and the non-reflected process?
I mean, originally it is proved. I mean, reflected process is a continuous function on the Canlet space. So if you can prove it for the original process, you can prove it for the reflected process converges as well. And also the excursion length is a continuous function on the Canlet space if you have some regularity conditions. So you can, from that, you can reduce component sizes as well. Okay, so I just skipped like probably 10 intermediate results, but sort of wanted to give you an idea. So the excursion length of this process will give us the rescaled component sizes, where component sizes have to be rescaled by n to the power 2/3 because time was scaled by n to the power 2/3, right? And our time indicated the exploration of components. So this implies the rescaled component sizes ordered convergent distribution to ordered excursion lengths of these stochastic processes that you get. Okay, so everything depends on whether you can prove this thing, but this is not a very nicely behaved object. Usually, if you have random walks, you can use functional central limit theorem to prove results like it converges to Brownian motion. But in this case, you can, so in this case, these are not like simple random walks, these are martingales. So you can use something called a martingale functional central limit theorem in order to arrive at this result. Sure.
If you don't reflect the process, then the negative parabolic drift, right, will just push you to minus infinity. You won't have like your ordered excursion lines, like you won't have positive things beyond the point. Right?
So the excursions are defined in a way that whenever you get back to the previous minima, that's your excursion.
Oh, you're effectively doing the reflected drop.
Yeah, exactly.
I see. Okay.
So
yeah.
So the reflect, I mean, the minimum process is always decreasing. When it hits the minimum, that's when you have explored a component. Right. This is a technique, but why should you? So first, revisit the method. So we explode the graph and encode component sizes in terms of a walk, and take scaling limits of the walk, and sort of recover the limits of the component sizes from the limiting process. That was the whole idea. Okay. In this case, you got this very nice Brownian motion, blah, blah, blah. But in general, you can also do the same technique for supercritical graphs, right? So when you are exploring supercritical graphs, if you rescale properly, the limit of the random graphs, limit of the exploration process would look something like this, because the component size converges and the exploration process also concentrates around a deterministic curve. And this hitting time will give you the size of the giant component, right? And actually, this method was applied by Janssen and Lubja for configuration models. You can check out their paper. Right. Summary, we are at the end. So we considered percolation and epidemics. And we saw that percolation can be coupled to the SIR epidemics. Then we showed that expected cluster size is like square root n, whatever be your graph. But then for dense graphs, this is the right threshold. Okay. However, sparse graphs, it's not. That's why studying epidemics on sparse graphs completely separately is super interesting. And the second part, we learned about a method called exploration process convergence, and use it to find non-degenerate scaling limits of component sizes at Erdős-Rényi at lambda equals 1. So for further reading, you can look at these references. Most of the things I have covered are in this book of random graphs and complex networks. For percolation and epidemics, you can look at this paper. For critical behavior, Aldous actually proves a lot of things in that paper. They look at critical window and evolution of processes over the critical window, like convergence to something called a multiplicative coalescent. So if you are interested in fascinating stochastic objects, feel free to look them up. And yeah, so you can also look at my doctoral thesis. And in chapter 1, there is a survey on what happens near the criticality, for many graph models. So you can look at the survey. Okay, so yeah, my goal was kind of to introduce you to many of these different concepts and also the techniques that we use usually in random graph theory. So hopefully you enjoyed it and learned something. Please let me know if you have any questions, or I am here for the whole semester, so we can always grab a coffee, right?
Thank you very much. That was a beautiful sequence of 2 talks. Do we have any more questions?
I have one.
Yes.
If I'm allowed. So you said in your dissertation, you did in your dissertation, you studied critical behavior for graphs with the prescribed degrees, let's say. So in the paper, Molloy and Reed, I don't think that they could determine the correct width of the critical window. Can you do something?
What we show is that if you look at, say, graphs with given degrees, then as long as you have a finite third moment condition on the degree distribution, you get the same limit as the Erdős-Rényi random graph. So there is universality.
So you get
In the
window
criticality,
and
mean?
the minus.
Yes, and over the whole window, so you get the whole window, so you get the whole multiplicative correlation process.
Yes. So my question was indeed the correct width of the window, like in the heterogeneous, we know that this should be, if you parameterize it by your parameter
So if,
lambda, then it should be width of n to
Yes.
the 1/3 or
Yes.
minus 1/3,
Yes.
depending on how you see the things.
right.
And
So
you get that.
it is lambda times n to the power minus 1/3 for heterogeneous. However, if you don't have finite third moment, it's a different thing. Width depends on the degree distribution.
Yeah, that's what I thought. Thank you very much.
Nice. Further questions?
I can just say it. So I know this is just an introduction. I really like this. In general, if you have a little bit of dependence in any sense, do some of these techniques carry over, or is it kind of go?
Correct. So they do. For example, if you are doing, say, configuration model, the edge connections are not independent. But you can apply this exploration process technique still, but verifying things like martingale convergence theorem, functional, those are quite difficult.
Well, let me sort of give an example. So what if it did the Potts model near Q equals 1, but Q is not exactly 1? So there you have a small perturbation of being independent, but you sort of multiply clusters by Q to the number of clusters, and Q is almost 1, but not quite. So you have a small perturbation of independent percolation.
Mm-hmm.
Do you have results like this?
So I don't exactly say the model you're saying. If you can define it, of course.
Okay, take your favorite model, like say the configuration model.
Okay.
Don't do independent percolation. Do percolation on it where the probability of seeing a configuration is multiplied by Q to the number of clusters.
Okay.
And Q is not 1, it's 1 plus epsilon.
I see. I don't know.
So that would introduce some interaction, right? So there are many, or you could have that at your vertex. Maybe it's more likely to have 3 edges. It's not just P to the power of, I mean, it's not binomial NP, but it's some other distribution of the degrees.
Mm-hmm.
So you get some small.
So in the random box,
kind of things you were thinking of?
I think there is a so-called random cluster model where number of component Q is weighted by this number of.
Yes, that was one example. But I mean, there are many models where you would have dependent percolation. But the question is whether maybe it would be super interesting if I could do something like that.
Yes. I mean, on top of my head, I definitely don't know how to prove scaling limit of the exploration process unless it is already shown in the literature. But definitely, we have to talk about it.
So the physicist would say if Q is smaller than 4, it should hold, right? Or in 2 dimensions, maybe at least, then it's conformally invariant.
Would you expect the same kind of limits, or?
I have no idea.
Okay. Yeah.
Okay, good. Thank you all. And
I still